Let me introduce our next speaker, that is Rafael Garcia Campos, that is the director of the Underwater Vision Lab at the University of Girona, here in Spain, and he's to present the work towards embedding intelligence in the Trawl. Okay, well, Rafael, thank you.
Thank you very much, Luis, and thank you for the invitation and give us a chance to present our work here. Let me start, first of all, by introducing my research group. We are basically a robotics team, and we develop technology for the exploration of the ocean. And this involves, on the one hand, building autonomous robots. So we want to embed technology in the robot so that it can react appropriately to the different situations it might encounter underwater. And on the other hand, we develop underwater vision techniques, either to improve image quality or to improve image visibility, such as in this case, in which our calibration pattern is hardly visible in the original image, and we can see it in the de-haze image. So what we normally do is to launch the robot, and the robot will carry out a survey in an autonomous way. In this case, this is a mapping survey. So when the robot reaches the seabed, it acquires images of the seabed that are normally used to build a map. And normally this map, when the robot comes back, will share this map with us, and then we can apply image classification techniques to detect interest areas, or sometimes we run the classification techniques directly in the embedded hardware in the robot. And we build these maps in 2D when looking at flat seabed areas, or in 3D when we're exploring more complex structures such as this hydrothermal chimney. But what I'm going to present today is based on the use of a division subsea unit, which is a device that it's directly placed in the trawl. And it's basically a vision system for identifying and measuring fish underwater. This is a development of a Norwegian company called Division. And this device allows to acquire stereo images at a frequency between 5 and 10 images per second. Currently, the images are being saved on a solid state disk, and we have developed a deep learning model to process these images offline. But in the same way that we do real-time processing with our robots, we are working on the hardware to process the images on board the Division system in the near future, which will make real-time active sorting possible. And here you see the first design of the gate to open the net. And here you see the current version, which is placed right after the Division subsea unit, which allows to close these gates here, and then the fish can escape through the openings on the sides, which are these openings in red here, and get out of the net if this is not what I want to catch. Okay. So here you have a view of the box and the place where we have the electronics and the stereo camera system. I should say that all the software that we are developing is a cooperation between Scantrol, Division, and the University of Girona, and a spin-off company called Girona Vision Research, which is the technological park here in Girona. And this subsea unit can be integrated in the Division Echo Viewer for evaluation after the trawl. So down you can see the echograms of the trawl, which can be synchronized with the images. And on the top left here in green, you see the depth, and on the right you see the trawl tow length. So you can analyze the trawl afterwards using this interface. So one of the first things we wanted to do, we wanted to solve at least, was to develop an automatic system to be able to count how many fish entered the net and pick some fish that it's fully visible to measure it using the stereo camera. So in this way, we would know what is the average size of the fish entering the net. And in order to carry out instant segmentation, we performed transfer learning using a Mask-RCNN trained with a COCO data set. The first step is the object detection, and the second step is the semantic segmentation itself. And since there are two phases, of course, we have two parts, one for object detection that we were using the faster RCNN using a region proposal network to determine the regions of interest. For semantic segmentation, we're using fully convolution networks. And we modified the last layer of the Mask-RCNN to learn how to detect fish. This is some of the data we were using and how we were splitting it. And these are some of the results. You see that when the number of fish that we have in the images is small, things are working fine. When we have small overlaps, this is still working in a high percentage in a proper way, and in some cases it's not able to segment or to carry out proper segmentation, and then we use an algorithm for gradient refinement, that it's able to do automatic fish detection and length estimation, even if even if the shape of the fish is not straight, we come up with a measurement. This is an algorithm that it's probabilistic. We don't always get the same result, and we are quantifying these results right now. So this is still an open issue. And some of here you have some of the results of the different models showing an average precision in the segmentation of 99% when the fish is isolated, and between 85 and 90% for occluding overlapping fish. And when we try this model with new trawls, the performance is very good when the occlusions are not or are moderate. But when there is more crowded scenes, we see that the performance of the system starts dragging away. But you see, in this type of crowded scenes, still the performance is not that bad. This is the segmentation of the Mask-RCNN, and this is the refined segmentation that we carry out on our using our system. And then, of course, we are looking at building an embedded solution. So we want this to run on a hardware in the Subsea unit. So we're using an NVIDIA Jetson Xavier with some PC104 and other electronics to carry out or to have an embedded solution for the next generation Trawl. And I should say that one of the main goals in this project is the development of a smart catching system. And you've seen that we rely on the deep learning based algorithms, and they are known to require large training sets. So one of the things that are worrying us is how can we feed the deep learning system with label data. And for this reason, we are developing what is called the Deep Vision Biobase. And this is a database of images and the associated labels of the information that it's already being gathered by research vessels. Especially, we're working, this is a collaboration also with the IMR Institute in Bergen. And these institutes that are using the research version of the Deep Vision system have some biologists that are currently acquiring hours and hours of fish footage, and they are labeling this data so that we have pixel level fish segmentation. We have the species and the size and the depth and the location, because when they do this, they use the stereo system of the Deep Vision Subsea unit, and they are able to carry out this stereo measurement. So we know we have ground truth of the size of the fish, and we also store the depth and the location where the fish was catched. And this is information that we want to integrate in the AI in the near future. And the idea here is that not only the fishing vessels, but also the scientific community would benefit from the data stored on the Deep Vision biobase. Okay. And just as a side comment, we gave it a try too to retrain a darknet YOLO to legacy videos acquired by industrial AUVs. And in this case, the videos have different levels of image compression and low contrast and limited visibility. But you see that in this case, this is also something which we have worked very little, but has some interest on our research group now. And then let me come to the conclusions. So basically, we've presented a model that can handle moderate amount of overlapping, occluded fishes slightly occluding each other, but it works very well for detection of individual fish, although it fails on very crowded scenes, as has been mentioned already in the previous presentations. Fish sizing is possible in moderate occlusion, but we have not yet quantified the accuracy of our sizing method. We're collecting images for that, but this got shifted lately due to other priority research that came to our table. And occlusion is still an issue, as proper instance segmentation fails to work very crowded and cluttered scenes. And finally, larger data sets are required for better generalization. So it's very important to have this effort of trying to come up with a common database that we can use, and then this will allow us to exploit deep learning and machine learning in general to another stage. And finally, in our case, we're exploring transformer architectures and few shot learning models, so which suit very well when you have a lot of data, but not all the data is labeled, and then we can exploit the results that we get out of these models. And that's it from my side. Again, if you want to drop me an email, I'll be very glad to further discuss any of these issues with you.
SICAPTOR, monitorización electrónica para una mejor gestión.